Okay, so this is the second lecture. In the first lecture, we saw essentially just the definition of what a semi-complete vector field is. And I promised you that there were some local abstractions for semi-completeness that we didn't see in the first lecture. So I will start this lecture by telling you some things that happen in dimension 1. And I will make first a statement about complete vector fields, and later I will show you that, in fact, this statement is a local one. Okay, so this will be a very elementary, basic statement. So let me just read it to you. So let C be a complex curve, X a complete vector field on C, and suppose that you have some point P, that's 0 of X, and I claim that in suitable coordinates around P, either your vector field is linear or your vector field is conjugate to this z squared d over dz. Okay, so that's a statement. So we have a global hypothesis, so completeness is something global, and we have a local consequence. Okay, so I will give you the proof of this fact. I will give you two proofs of this fact. So the first one will be really in a global, from a global point of view. First of all, if you have a flow, you have orbits, and these orbits are quotients of C under some discrete subgroup of this additive group of C. So your integral curves are your integral curves are elliptic curves. That's one possibility. The other possibility is that they are cylinders. So these orbits have two ends. And the other possibility is that the stabilizer is trivial, and then you have here. So this is C over some multiple of Z, and this is C mod a lattice. Okay, so these are the three orbits that we see. Okay, so let me also consider, so these are the three orbits, and so of course, if we have the first one, an elliptic curve, we won't see any zero of our vector fields. So what I will say concerns mostly the two others, the non-compact ones. Okay, so let me now consider in C the vector field lambda z d over dz. So I can consider this in Z or in P1. So this vector field compactifies into P1. It has one singular point in 0. And I can tell you, I can integrate this vector field. So I can tell you that a solution is given by e to the t maps to the e to the lambda t. Okay? So the stabilizer here is of the form 2IP, is generated by 2IP over lambda. So this is the stabilizer of this vector field. Okay, it means that all these cylinders, all these orbits are represented as lambda varies in this family of vector fields in CP1. Okay. So if I had a way to add a point, a pink point, along this end of the cylinder, then, well, that would be one way of adding a zero. But I know that one way of doing this is through this linear vector field on P1. And then by Riemann's extension theorem, if I have a way to compactify it up to a holomorphism, it is necessarily the one that appears through this compactification through the linear vector field. Okay, so if I have more generally a zero of the vector field and I have an orbit where I have some period, then necessarily I can put it in correspondence with this linear vector field. And so in the neighborhood of the equilibrium point, your vector field will be this way. Okay? So let us see now what happens in the second case. So here, this vector field, this is given by the vector field d over dz, this orbit, and then it can also be compactified into P1 by considering the variable w is -1 over z. So in this new variable, it turns out that your vector field reads omega squared d over dz. Okay, so this orbit has one end, and in P1, I can also just can compactify it into P1 by adding just one point. And when I do this, I will have this vector field. And the same argument applies. So if I have now a vector field and I have an isolated singularity of my vector field somewhere, and I find that the integral, the period of the solution is 0, as it is in this case, because the period here amounts to drawing a big square here. It has trivial period, it has trivial stabilizer. So if I have a trivial period, then I have a whole orbit, and then I can put it in correspondence with this orbit at infinity. By Riemann's extension theorem, there's only one vector field that can fit at infinity, and this vector field is, again, omega squared. Okay, so this gives our first proof of this statement. Let me read it again. Let C be a curve, a complete vector field, and C, and an isolated singularity, and a singularity of this vector field, so it's either linear or z squared. Okay, so let me give you now another proof, sort of a local proof. So this is very fairly elementary. So we understand a lot of things about the C and the quotients and the discrete subgroups. So just for the principle, let me give you a local proof of the same result. Okay, so I will give you this second proof. So the proof will use the things we know about local forms of vector fields in dimension 1. So we know that in dimension 1, a vector field, either it has a non-trivial linear part, and then it is linearizable, or if it doesn't, then it has just two invariants. The first one is P, is the order of the zero it has. So you have the P here and also the P here, is the order of the zero, and it has another parameter alpha that I will show you what it is. So if you have a holomorphic vector field in dimension 1, and you have a singular point in some coordinates, it will be one of these two vector fields. Okay, so these are the normal forms. So I have to show you in order to prove the theorem that in the second case, if I have a semi-complete vector field, if one of these vector fields is part of an action, I would have to show you that then P equals 1 and alpha equals 0. So this is equivalent to the statement I showed you. So this is what I want. I want these two things to happen under the hypothesis of completeness. Okay, so let's go. So I will suppose in the second case, I will just try to show you that alpha cannot be equal to 1. Suppose that it is equal to 1. Okay, now the time form that I have, remember the time form is the time form dt is just the time for that evaluated on x is a constant 1. So the time form has these expressions 1 over z to the p plus 1 over z. As you see, the time form has the residue around 0. Okay, so let me consider, instead of integrating this into a so let me consider this function f that maps my vector field. So I have here is where my x lives, and then I have another c, which is where the vector field z d over dc lives. This also has d over dz. This also has singular point, and the time form of this vector field is dz over z. Okay, so they have the same period. So I have a well-defined map from one to the other because I can integrate it, and if I make a turn around the origin and at the left, and I will map to a turn around the origin in the right. So I have a well-defined function. Okay, so I claim that if my vector field, my original vector field X is semi-complete, I claim that this map that I call F, I claim that this map will be one-to-one. So suppose that you have 2 points here, P and Q, and suppose that they get mapped to the very same point here at the right, okay? So I'm using the hypothesis that my vector field is semi-complete. It will be so because I'm trying to understand singularity. My hypothesis at the beginning is completeness, okay? So now, so if I take a path that joins P to Q here, under F, it will be, of course, mapped to a closed path. Okay? So closed paths have a period, and closed paths at the left have the same period. So I have at the left some period, say, starting at P, that makes some number of turns, and then it gives you a closed path, in such a way that when I take the purple path and then the green one, I get a path. So the concatenation of the two will give me a path gamma, and I claim that the integral of my time form along gamma here is 0, right? Because here the integral from P to Q along the green line is the same thing as I obtained by turning some integer number of times around the origin. So the integral of my time form at the left is equal to 0, and it's a path that goes from P to Q. So since my vector field is semi-complete, this is my fourth condition, this integral, and this integral is 0, then then P must be equal to Q, okay? Because otherwise, so this implies that P equal Q, under the hypothesis that my vector field is semi-complete, okay? Good. So my vector field is my function F that I wrote here is one-to-one, but this tells you that it extends. It does not have an essential singularity at 0. It extends as some holomorphic map to 0. So to the right, I have a vector field that has a non-trivial linear part. This is a contradiction because this map F, which is one-to-one and extends holomorphically to 0, should conjugate the 2 points, the 2 vector fields. And I know that the 0 on the left is a very degenerate one, and the 0 on the right is not a degenerate one. This is a contradiction. So this shows that we cannot have the hypothesis of semi-completeness with the hypothesis alpha equals to 1. Okay, and the same thing is alpha is non-zero. Okay, so this argument proves that if your vector field is semi-complete, then you should have alpha equal to 0. So let us show now that P must be equal to 2. Okay, so let me pass to the case P equal to 0. And so I have this vector field here, Z to the P plus 1, D over dz. And it turns out that if I consider this map that maps Z to the P, it maps this vector field to the vector field omega. So up to a constant is just the vector field omega squared D over d omega. Okay? So this you can check this directly. So, and here, as we said, this was to the right, this omega squared d over d omega was the vector field that we used to compactify the vector field without the orbit without a stabilizer. So if I take a path, again, a path gamma, a closed path this time, of course, the integral of the time form along gamma, the time form of this vector field to the right will be 0. Okay? It says that it's once again saying that this vector field is the one used to compactify the orbit which has trivial stabilizer. But then I can say if I will make the drawing if P equals, I don't know, okay, so 4, P equals 3. Okay, so if P equals 3, when I take the lift of gamma here, so I will get a sector of some angle 2 pi over P. So when I take, so I will have another curve. This will be the lift of gamma. And the thing is that, well, if this map, Z to the P, maps one vector field into each other, it should make the time forms, the corresponding times form, map one to each other. So I get to the left, I have that the integral of this time form, this time along gamma tilde, is again equal to 0. Okay, but to the left, this is not a closed path. So this vector field cannot be semi-complete. And this proves that if I have if I have P different from 1, this is a proper sector. There's no chance, there's no way in which this lift of gamma can be a closed curve. So the vector field cannot be semi-complete. Okay, so this is this finishes the proof of this statement. And the advantage of you having the video is that you can go back and just see the slide for the statement. Okay, so I'm telling. So the word to advertise all this will be this one. So germs of degenerate semi-complete vector fields are very rare. That's what we just saw in dimension 1, and this will be the motivating line. So if you have, what we saw is that vector fields with a non-degenerate, in dimension 1, vector fields with a non-degenerate linear part are all semi-complete, are all local models for complete vector fields. But those that have a degenerate linear part, in general, they are not semi-complete. Okay, so this is the advertising line, and this is what we will try to. I will try to show you how this works in dimension 2. Okay, so up until now we have some definitions and we have some things in dimension 1, but let us go to dimension 2. Okay, so in order to illustrate how this works, let me show you what happens with the simplest, in some sense, the simplest degenerate vector fields in dimension 2. So we're going to semi-complete vector fields in dimension 2. Okay, so I will tell you this. I will tell you about this theorem by Giulio Revello. So what we mean by saddle node for vector fields, we have vector fields as in the statement of the theorem. So imagine that you have let us omit this semi-complete for a while. It would be important, but let us omit it. By saying that you have a saddle node, I say that X has an equilibrium point at 0, whose linear part has one vanishing and one non-vanishing eigenvalue. This is what a saddle node is. And suppose that, furthermore, you have such a saddle node, and it is a semi-complete one. Okay, suppose that, for example, that you have a global vector field, a global complete vector field, and you look at a singular point and you see a saddle node. So what this theorem tells you is that up to multiplication by some non-vanishing holomorphic function, X has a very particular form, and it has this form. It has that is written in the slides for some integer lambda. Okay, so if you're acquainted with the normal forms of the saddle node, you will know that saddle nodes are orbitally very, very complicated. They have a very diverse behavior. They're a difficult family of singularities. They are very well understood, but you need some. You cannot reduce them to such a formula like this one. And under the hypothesis that the vector field is semi-complete, you can actually give this normal form, this orbital normal form. Okay. So let me just tell you one or two things about this theorem of Rebello on saddle nodes. Okay, so saddle nodes, we have studied them from a long time. So we have Dulac made a very deep study, and then we have Huku, Hara, Kimura, and Matuda who made many more. And then I have some points here because there's a lot of work on the saddle node. We understand it pretty well. So Dulac tells you that up to a factor, you can holomorphically put your saddle node in this form. So this means, say, when I see this right here, it means that I will definitely have y equals 0 that I'm drawing here. So this is the x-axis, y equals 0. That will be an orbit of your vector field. This is called the strong separatrix, the strong invariant curve. Okay, so and the thing is that all the other curves, and I have a projection. Let me write this projection. So I'm cheating here because I'm writing. So this line at the left is what when real two-dimensional orbit. So let me just project to the y equals 0 here. And what this first thing says is that this projection is transverse to the leaves other than y equals 0. So this is the first thing that follows from this first fact from Dulac. Okay, so this is up to a factor of an invertible holomorphic factor, but let me just forget that it's up to a factor, and let me just think that it actually projects my vector field onto the vector field y to the p plus 1 d over dy, okay, just for the sake of the argument. So we know that this vector field, this projection, is not semi-complete, and we know that there are sectors of angle 2 pi over p, and that in these sectors we can draw curves. Let me draw one in green, like this, sort of like this, where we will have, for the integral of the time form is 0. So if I could lift, so I know that this projection is transverse to the leaves. So if I could lift this green leaf to the curves, to the integral curves, then I would essentially prove that I should have p equal 2. Okay, so that's first thing. So in general, what we know is that we have a formal normal form. This is that we can write in this form. And you see in this formal normal form, I have some special curves given by x equals 0. And when you see the theory by the study made by Kuhara, Kimura, and Matuda tells you that, well, we know since a very long time that this formal invariant curve doesn't actually exist, need not exist in the integral curve, but we can see that along some sectors, there are some sectors. Okay, so some things that project. So let me draw it again. So we have some sectors along which we really can define this integral curve, that's sort of like this. And if you're careful enough, you will see that, in fact, these sectors that do exist by the study by Fukuhara, Kimura, and Matuda map into some sectors that are essentially of angle 3/2 of 2 pi over p. Okay, so we can definitely have in these sectors, we can fit these sectors of angle 2 pi over p, and along these sectors we can lift. So we can lift these curves here, and this shows that if you have a saddle node as here, then you will necessarily have p equal 1. Okay, this is similar to the first one. So this is the first part of Rebello's statement. The first part is that is not too degenerate. You have some y squared here. And so this is the beginning, and then the same argument I showed you shows that this weak separatrix, this invariant curve that need only exist at the formal or sectorial level actually is globally defined, because if not, you would have an open curve in it along which the integral of the time form would be 0. And if you work more, you will find that not only that, but that your this lambda, which is in principle a complex number, would actually be in Z, and so on. Okay, so I not wish to enter more into these details, but just to confirm this in this setting, this thing that I said before is that the germs of degenerate vector fields are very rare. In these vector fields, which are among the degenerate ones, the least degenerate ones, because they have one non-vanishing eigenvalue, and these ones, they cannot be too degenerate, and we understand them fairly well. Okay, so this is what happens with saddle nodes, and I sketched some parts of the proof. Okay, so let me now go to another one of Julio's results that goes also in this direction, that degenerate vector fields are almost never semi-complete. Okay, so in dimension 1, we saw that the vector fields were just either had a non-trivial linear part or have a non-trivial quadratic part. We do not have semi-complete vector fields that start with order 3. And this is also the case for vector fields on surfaces. Okay? So this is also the case for vector fields on surfaces. So the theorem is this one. Suppose that you have X is a semi-complete vector field in a neighborhood of the origin in C2, and you have 0 is an isolated 0 of X. So if you take the Taylor development of X around the origin, you can say it starts with a jth term and then a j plus 1 term. Rebello's conclusion is this j is equal to 2. Okay, so if you have an isolated singularity of a vector field, it cannot start at order 3 or more. It has to start with a linear or a quadratic part. So let me give you the proof of this, and the proof is very, very, very simple. So we have a result of Camacho and Sat that tells you, if I have here my vector field X, tells me that I have here a curve that is invariant by the foliation here. So the drawing, probably this one. And I can have a curve. This is a parametrized curve. So I have here a 0, and I can parameterize this curve. This is not a solution to the equation, just a parametrization. I have this foliation to the right. This is the theorem of Camacho and Sat. Okay, so if I have this, I can just, since I have a vector field that's tangent to this curve, this separatrix, I can pull it back here. So I can have here a vector field y. It's a one-dimensional vector field, and if it starts with, say, some kth part and then some higher order terms, when you see what happens is that this k is greater or equal to j on the one hand. Okay, so this j is the one in the statement. On the other hand, you know that if your vector field in the right is semi-complete, then it should be semi-complete in restriction to every leaf. But if it is semi-complete, then you have that k is smaller or equal than 2. This is what we just proved, that the germs of semi-complete vector fields cannot start with cubic part. So k is at most 2, and k is bigger than j, so j is at most 2. Okay, so this is the proof of the theorem. You use the Camacho-Sat separatrix theorem. You restrict the vector field, and you use what you know in dimension 1. So we think that this result is also valid in dimension 3. In dimension 3, we do not have the Camacho-Sat separatrix theorems. There exist examples of vector fields by curves without separatrices, but we think that none of them are semi-complete. Okay, so probably this works as well as this holds in dimension 3 as well. Okay. Okay. And you get from this proof, so let me come back to the proof, you get more things. For example, you get that if j equals 2, then actually the separatrices must be smooth. They cannot have cusps. They must have a definite tangent. Or, for example, that if this k, so I will use this in what follows. Also, when you look what happens and how does this degree change when you parameterize, when you look at the vector field x and how it restricts to the separatrix, one thing that you know is that one thing that you can see is that, for example, if k equals 1, for example, if you have a linear vector field, is because you also have that j equal 1, okay? So that we will use this later on. Okay, so this is a theorem of Rebello. We do not know if it's true in higher dimensions. We suspect it. We suspect that this way in which vector fields cannot be too degenerate holds in higher dimensions. Okay. So let me use all what we have said until now to give you a statement. So this is part of the statement I show you in one of my first slides in the first lecture. Okay. So suppose you have a Stein surface. And suppose you have a complete holomorphic vector field on this Stein surface. And suppose you have a point that is an isolated zero of x. I claim that in that case, the x is a non-degenerate singularity. Okay, so let me prove this. Okay, so let me draw this. This is P. This is the singular point. Okay, so you have a complete holomorphic vector field, and you're in a Stein surface. Okay, so this vector field, as all the other ones, all the other vector fields in dimension 2, has a separatrix. Draw it here. Okay, as before, by the theorem of Camacho and Sat, you have a separatrix, and you can restrict the vector field to the separatrix. Okay, now suppose that in restriction to the separatrix, well, the vector field is semi-complete. So in restriction to the separatrix, it will be semi-complete as well. So it is either conjugate to omega squared d over d omega, or just some lambda omega d over d omega. So these are the two possibilities. We already saw this. So suppose we're in the first case. So if we're in then let me draw this here. So if we're in the first case, I said we have a point that is compactifying an orbit. And if we are in the second case, we know that the period is 0. Okay, so the only way in which this can happen, this thing I'm writing here, is that the orbit is a copy of P1 of C, and that this point is a singular point. Okay. So if this is what happens, then this P1 should be a submanifold of my Stein surface. But Stein surfaces are the surfaces that embed into some Cn. They do not have compact submanifolds. You cannot have a P1. So since you're in a Stein surface, this case cannot arrive. Okay. So the argument again is that if you have a quadratic part, it necessarily, if you're in a complete vector field, it comes with a P1 with a compact orbit, and you can do nothing about it. Okay. Okay. So the first one cannot happen, and then so we are necessarily in the case where the restriction of the vector field to the separatrix has a non-trivial linear part. Okay. So what can happen if well, either I already have a, so this implies if you look carefully, this implies that the second condition implies that your vector field has a non-trivial linear part. So this the second condition means that X, the vector field here at the left, has non-trivial linear part. X has non-trivial linear part. So two things can happen. So either your vector field is non-degenerate, and then you're done. Or if it's not degenerate, it is a saddle node. Okay? So if it is a saddle node, let me come back to Rebello's theorem. If it is a saddle node, then you have two invariant curves, one corresponding to x equals 0, and another one corresponding to y equals 0. And when you restrict to x equals 0, you have a vector field y squared d over dy. Okay, so if you're coming back to here, if you have a saddle node, you have already one separatrix that's actually smooth, along which your vector field is lambda w, but then you have a second separatrix, a green one, along which, in restriction to which, you have y squared d over dy as a restricted vector field. Okay? But the same argument as before that ruled out the existence of quadratic terms along separatrices tells you that you cannot have, in a complete vector field in a Stein surface, you cannot have such 0. Okay? So this shows you that your singular point x that has a non-trivial linear part should actually have a non-degenerate one. Okay, and this proves this theorem. Okay, so you have we understand very well, as you see, we have this local analysis allows us to say things about how in a specific setting, in this case Stein surfaces, how these are. Okay, so this is an example of such things, and let me give you another example of that illustrates this model that we show that degenerate vector fields, semi-complete vector fields, cannot be too degenerate. Okay, so our previous theorem tells us that, this is the previous one, that if I have a non-trivial, if I have a vector field with an isolated singularity, then it cannot start with order 3. It cannot start at the cubic term. So what if the vector field starts with a quadratic part? This is the content of this theorem by Gis and Rebello. It tells you, well, suppose that you have in C2, in a neighborhood of the origin, suppose that you have an isolated equilibrium point, and you have that your vector field x does not have linear part. So the first jet of x at 0 vanishes. You know that from the previous theorem that your quadratic part cannot vanish. And what this theorem tells you is that, you know, under this situation, almost everything about the vector field. It tells you that up to multiplication by a non-vanishing holomorphic function, you know, x can only be one of these countable examples. So either belong to the first family, the first part here, or belong to or be one of these three sporadic, these three particular cases. Okay, so let me just finish this second session. I will tell you a bit about this, but as you see, let me just point out that all these vector fields that appear are homogeneous. So these are quadratic homogeneous vector fields. And this is not part of the hypothesis, this is part of the conclusion. Then the x is giving up to a holomorphic factor, non-vanishing holomorphic factor by some homogeneous vector fields. And let me just finish this session by telling you where do these homogeneous, one source of these homogeneous vector fields, using what we saw before about the closeness of the space of semi-complete vector fields. Okay, so suppose that you have, and this is part of, this was used by Panlevé thoroughly, this is Painlevé's alpha method. So also, you can see it this way, but and this what I will write here is a statement also by Rebello. So suppose you have a semi-complete vector field in a ball around the origin in C2, and it has a trivial inner part and a non-trivial second jet. So you have a vector field that starts with a quadratic part, and its germ at the origin is semi-complete. There's some neighborhood of the origin where it is semi-complete. And what I claim is that it's the polynomial vector field given by its quadratic part gives a semi-complete vector field in C2. Okay, so, and this is a proof. So consider this homotopy that just multiplies the coordinates in C2 by alpha. It maps B to alpha times B if alpha is bigger than 1. So it does this. It is this homotopy linear in each coordinate multiplies both coordinates by alpha. Okay, so let me consider the Taylor development at the origin of this vector field. So this is, I took the homotopy applied to my vector field X, and then I just divided it by alpha. So when I take the homotopy, I do not change the semi-complete nature of my vector field. When I multiply it by a constant, I do not change the semi-complete nature of the vector field as well. I will just multiply my vector field by a constant, say I will multiply my time phone by a constant, but if I had a path along which it was non-zero, it will remain non-zero. So if I take this vector field, I have a vector field, and I take the Taylor development at the origin, it will take this form. It will start with the quadratic part, and then the cubic part will be multiplied by alpha, the quadratic part by alpha squared, and so on. So, and this, if I take alpha going to 0, I will get a bigger and bigger vector field defined in even bigger and bigger balls. So when I take the limit, it will converge to a quadratic vector field defined in a very big domain. As big as it will converge to C2. And then by the previous result that I talked to you about, that these the space of vector fields is closed, since for all alpha my vector field is semi-complete, then it will be semi-complete in the limit. So your vector field will be a quadratic vector field in C2 that will be semi-complete. And this is one way in which semi-complete homogeneous vector fields appear. So one of the ideas for this proof is take your semi-complete vector field, zoom in, see what the first quadratic part is. The first quadratic part will be one of the ones you're looking at, probably some more, because in the limit, the singularity need not be isolated of the limit vector field, and then start taking this homogeneous vector field as a model, and then try to understand what you lost in the process of zooming in. Okay, but this goes right in the direction of what I was telling you, that the semi-complete vector fields are not very degenerate, and those that are degenerate can be understood pretty much. Okay, so with this, I will end the second session, and I will meet you again for the third session of this series of lectures. Thank you very much.